Hello everyone and welcome to a new discussion which we are going to continue on that groundwater modeling. So, in the previous discussion we have introduced this concept of groundwater modeling in that title groundwater modeling 1. Now, we are going to discuss further on this, and at the end of this discussion we will be also discussing few available options in terms of software for groundwater modeling and some output also I would be showing to you. So, first as you know that we have been discussing about different kinds of modelings in previous discussion. So, like numerical solutions of governing equations. So, in order to solve these groundwater flow or transport equation which governs these equations, for example, compute hydraulic head or solute concentration as a function of x, y, z and t with the time is also important in our groundwater modeling. So, we need to know what we the important parameters like aquifer parameters and then groundwater source sinks if they are, and the boundary conditions are also very important here, and that we will be also discussing. An initial condition, what is the initial conditions, what are the boundary conditions and other thing. So, this basically is the input which is required for this kind of modeling. So, the information which is essential to fully define and solve a transient subsurface flow or transport problem, and transient means here only for that time which we will be having in our model. So, t is there x, y, z and t. So, to solve a transient subsurface flow, because we are concerned only for the groundwater modeling. So, it has to be surface flow, subsurface flow or transport problems if there are any. So, these governing equations for numerical solutions that applies within the domain, that is we convert the physical problem into a mathematical one, because our groundwater flow and other conditions are basically physical problems below the subsurface. So, we try to convert through this in numerical modeling into mathematical one. Also the size and shape of the region of flow where or you can say the shape and size of the aquifer also. So, that is mainly from flow point of view. So, this is a flow domain as we mentioned, and conditions of boundaries. Boundaries are important in such modelings, and we will be further discussing on what our mean is boundary here of flow domain, that is the boundary conditions. So, in also we say what are the boundary conditions of a particular model, and initial conditions as also just discussed that within the flow region, and that is we would like to know what are the initial conditions of an aquifer, if because we are doing for groundwater domain or groundwater purposes, and spatial distribution, how these are distributed in space about the aquifer parameters. So, all these information are essential to fully define and solve a transient subsurface flow. And finally, a mathematical method of solution, and these can be FDM, FEM, finite element modeling or MOC or some other types of modeling. They all are under this numerical solutions. So, for this of course, the computer programs are used to solve these mathematical equations using initial and boundary conditions, and also initial conditions are not required if we are going for steady state problems. So, steady state and non-steady state, all those things we have already discussed in our previous or in earlier discussion. So, I am not going to discuss that part here or going to repeat that part here. And then third is the set of commands in the programming, because it is program. So, you have to have commands which will be used to solve the mathematical model which has been developed by through a computer program as is known as computer program or computer code. So, nowadays also instead of saying computer code or computer program, more popular term is coding, and this coding is generic, and hence it can be considered as a generic model. that means that it can be applied for other kind of solutions as well. That is what the generic means here. So, a generic model is applied to represent a particular geographic area by specifying a set of boundary and initial conditions. And that means that if a model has been developed, a computer based numerical solution has been developed and it is in generic form, then depending on the area, depending on the boundary conditions, initial conditions, size specific grid dimensions, because most of these would be working as raster or in grid dimensions. So, basically they are exploiting the concept of mathematical matrix as well as site specific parameters, values, hydrogeologic stresses and resulting computer program which is known as site specific model. So, we can have a generic model, we can have a site specific model. And so, if regularly on one area this has to be run, then it becomes basically site specific models, lot of parameters then are fixed and the rest of the things which are for a particular time of the year or boundary conditions may also be fixed in that case for a site specific model. Now, these generic computer codes are also available for numerical modeling for groundwater flow and transport processes, and these examples of these already developed models or computer programs like MODFLOW, very popular one, FEM flow also there, and FEM water. And these are the very popular computer programs or models which are available, and these can be used for different groundwater systems in a study area without modifying the source codes, because everyone cannot be expert of that. So, whatever the parameters it will ask, whatever the inputs it will ask these models, if we can provide, then we need not to go at that level of code changing codes and other things. But in certain conditions, when initial conditions of a requirements of a such models, software based models are not meeting, then probably we have to do some modification in the computer program itself. So, now we will discuss what basically our here boundary conditions meant here. So, boundary conditions, this boundary means a geometrical configuration of a surface enclosing the model domain. So, what are the enclosures or boundaries for this? So, boundary conditions must be specified for solving a mathematical model, initial conditions and boundary conditions. And boundary conditions basically constrain the problem at hand and make solutions unique, because for different areas in subsurface conditions are different, and therefore, once boundary conditions have been defined in a model, that becomes a specific or site specific model for that particular solution. So, that is why that solution becomes unique only for that, specific to that site. Mathematically, the boundary conditions include the geometry of boundary and values of dependent variables or its derivatives normal to boundary. For example, here what we are seeing is a model, a typical example of a model having boundary conditions. And what are the boundary conditions? Like here, semi pervious leaky, or we can say also leaky aquifer, and this is because of a fault, and this fault, though it is a alluvium fault, in Indo-Gangetic plain similar kind of situations are, or at many places similar kind of situations can be found, that within alluvial plain, Indo-Gangetic plain, we are also having faults, and these faults may have deposits or sediments which are impervious, means clay rich sediments might be there because and the faulting is there. So, that becomes a boundary. That boundary, that means it will not allow flow of water from one end to another or through it. That is why it is one type of boundary. Another type of boundary is this is the constant flux or no flux, because of you are having a completely impermeable bedrock. And if you go much deeper in the Indo-Gangetic plain, then this is what people expect, that we might be getting consolidated rocks at the basement rock. So, at the bottom also it becomes a boundary, bottom boundary condition. Now, here constant head, because you are having a stream, a river, and as you can see the water table is here. So, that means that also becomes a boundary condition, and this river if it is effluent, then it is recharging your groundwater regime continuously. That is why a constant head, a difference between the water table and water level in the stream, that can also become a boundary. So, these stream channels in hydraulic continuity with aquifer are there. So, they can also become boundary. Other is because when we are doing modeling, then we have to restrict our model for a particular area, and therefore, at some ends we will have a open or infinite boundary, and that is what it is shown here. So, that also becomes in some way a boundary. So, these are the different boundary conditions, and depending on subsurface formations, these we have to bring into our model, so that whatever the estimates about the groundwater flow and other things which through these models we get the prediction should be as accurate as possible. So, three types of boundary conditions are encountered generally. First is the constant head boundary, as you have seen in the figure, when head or concentration is known for surface boundary model regions, for example, ocean, sea, river, lake, direct hydraulic connection with the aquifer. So, little different boundary conditions will be there if we are working in a coastal area. So, that is why it is said that the solutions are unique for that particular location, or solutions are site specific, unique solutions are there, because these conditions will change, the aquifer's characteristics will change, basement rock might change, and therefore, the different solutions have to be adopted for different areas. Second type of boundary conditions is constant flux, which we have seen here, and that basically no flow through this boundary. When flow rate flux is known across surface boundary, the model region, that is groundwater divides, streamlines, impermeable faults and impervious subsurface layer, like here which we are seeing impervious bedrock. So, these also makes boundary conditions, and last type of boundary conditions can be mixed boundary conditions, that if some combination of head and flux of concentration and mass flux is known for surfaces bounding the model region, and for example, semi-pervious subsurface layers, that is a leaky confining, which we have already discussed, leaky confining or leaky aquifers, and which are having semi-pervious subsurface layers, maybe leaky confining layers, and semi-permeable or leaky faults. So, these kind of situations can be encountered in a subsurface condition. So, they will make our boundary conditions in a model. I said that in Indo-Gangetic plain these kind of faults are very common. Lot of work has been done or being done also extensively to find out these faults. Generally, people think that in alluvium the faults might not be there, but there are many faults are there, and which creates may create the boundary conditions if some impervious layer in between in a groundwater modeling, or they may create hindrance in case of groundwater flow. Now, another point which we also touched initially, that is the initial conditions. So, after boundary conditions, initial conditions are simply the values of dependent variable specified everywhere inside the boundary, that is model domain at the start of a simulation. Because see, the ultimate purpose of all these modeling to predict our groundwater flow and other things. So, that is why these are also one can say a simulation of the real situation. So, generally the initial conditions are specified for in a steady state solutions, and however the initial conditions are specified so that transient flow is occurring in the system at the start of simulation, and it should be, that is why it is called initial condition. So, these should be specified at the start of solution, and these should be recognized that the head or concentration will change during simulation, because everywhere things are not constant, and not only in the response to new pumping stress, but also due to initial conditions. Since initial conditions might change during the simulation, so that kind of incorporation in the model has to be also done. Now, another important point which comes after once boundary conditions have been designed, initial conditions have been obtained. Now, calibration, each model has to be calibrated. So, the output which will come would be more accurate output. So, calibration means here is that is necessary because of real world hydrogeologic systems are poorly known, because these are subsurface systems, and many times we do not have much details except through subsurface geophysics, or maybe due to test drilling and other. But these are also representation, they might not be giving you full knowledge about hydrogeologic systems in the area. So, in this model calibration, what is done is this is the process in which model parameters are adjusted. This is what the calibration is. When suppose there is some instrument or some other things which comes, that is initially it has to be calibrated, and for which you need some standards. For example, somebody have bought a watch now, or is a digital watch. Now, you want to calibrate. So, one of the best source for calibration or standard time is available nowadays through GNSS technology, or some people also called GPS, but that may not be very accurate term now. So, GNSS technology. So, you calibrate your timing or digital watch through GNSS or through internet. So, that is also one kind of calibration. So, in these groundwater modeling, the calibration is the process in which model parameters are adjusted until the model output matches the field observation conditions. So, it is a kind of iteration process, and once you have get that satisfactory answers, then you accept that the model is working and calibrations are now all right. For example, in a groundwater flow modeling, calibration is usually accomplished by finding a set of system parameters like K, hydraulic conductivity, and storativity and other things, and other poorly known inputs. For example, recharge and leaky streamed or aquifer, because recharge might not, information about recharge characteristics of an aquifer might not be there. So, these will produce simulated values of hydraulic heads and or flux, and that will match the measured and observed values within a specified range of error. So, now when error comes, that is another issue which we will be discussing next. So, what it is being done in the calibration ultimately is that we are comparing our outputs through a model with the real observations which have been done in the field. And of course, these observations are might not be extensive and may not be accurate as well. So, sometimes we do not know whether the data which has been collected in the field is accurate or the model outputs are accurate. So, these things have to be calibrated, basically have to understood, and then we have to find out what is the specific range of error in a particular area for a model. So, calibration, sometimes known as parameterization or parameter identification, that means which parameters of like which aquifer characteristics is influencing more, which boundary condition is influencing more or having more influence, and the initial condition another thing. So, these parameters are now will get established through this, that these are the key parameters for a particular area, for a particular site, that these are having more control over output. So, this model calibration can also be performed by either trial or error method, or as I have said, iteration kind of method, or automatic techniques are also there which can use the inverse computer code to do this kind of thing. More sophistication is being added nowadays for in the groundwater modeling also. So, this like automatic techniques are also becoming part of calibration in groundwater modeling. But you see that what we are discussing here, groundwater modeling in a completely generic form, and therefore, there are no hard and fast rules for deciding a good calibration accept the errors between observed and simulated values. So, depending on the area, depending on the subsurface condition, these calibrations will get affected accordingly. So, it is a kind of trial and error kind of method, and once the observed and simulated values are coming close, then we accept that this model is working for this particular area nicely, and then in future we need to just feed those basic values and we get the results for different seasons or for the transient times also. For calibrations, we can involve statistical goodness fit criteria, and also for error estimations for evaluating the performance of a model, and for which mean error or bias or biases mean absolute values exist, that is MAE. Root mean square error is also one of the very popular method to find out this about the errors. Coefficient of determination, that is R square, and Nash subsurface efficiency are also called model efficiency, are often used, because after all everyone wants that whatever the model giving, whatever the outputs a model is giving should be more close to the real things. So, that is why different techniques can be used. So, other than statistical goodness of fit criteria that facilitate the quantitative evaluation of our errors or fitting of the data, qualitative evaluation is also possible for evaluating these performance of these models. Qualitative evaluation, when one go for this, one goes for the qualitative evaluation, that means visual inspection of observed and simulated values in a certain graphical ways. That means the data one can plot and then can see where the variations are coming in the our simulation output and your real values. So, for example, simulation plots of observed and simulated groundwater level or concentration hydrographs, there is scatter plots, plot of residuals and contour maps etc. can be prepared for purpose of qualitative evaluation of our performance of a model. Now, last step in this one is verification or validation. Once the error part has been taken care that we have achieved a minimum possible error through a model while comparing these two outputs, one is simulated one and one is the real one, because real one is a representative only at few sites only. So, therefore, after that last step is validation. So, this is a test usually done so that we ascertain that the model is valid representation of hydrogeologic or subsurface systems which are being studied for a particular area, and that can be done by this. Before that we discussed that what is the process. So, this process of validation or verification in which the calibrated model is shown to be capable of reproducing a set of field observations in which independent of that use in the model calibration. So, by which you can know whether the model is working all right or not. So, for this we use this process in which calibrated model is shown to be capable of reproducing a set of field observations. So, here now no field data will be used, but only the model data will be used, and then that becomes our checking or verification on validation. And these validation results are also assessed using our quantitative, which we have just discussed, using statistical methods, and of course qualitative criteria as also there by plotting and using different types of plots like graphs or these scatter plots and other things. Further, under this validation verification, many times it is observed that the field conditions are not reproduced with the desired degree of accuracy by a model which has been developed or site specific model which has been developed after calibration. So, that means the model parameters should be changed, and then recalibration of the model should be done, with a new set of model parameters, and then verification should again be repeated. So, again that is what I said earlier also, is a kind of iteration process, and till we reach a satisfactory results and comparable results with simulation and field data. And finally, this eventually after iterations and several forward and backward processing, a result is results in a calibrated and verified model for a particular study area. Particular study area, this is a site specific solutions we might be putting. Now, further to ascertain that how good the modeling work is going on, or model is simulating, producing the simulated data, final step in groundwater modeling is sensitivity analysis, and there are various tools are available, various approaches are available for sensitivity analysis. So, for a well calibrated, well verified site specific model can reliably use for simulating or predicting future management. I am saying repeatedly, model is for future prediction or prediction, which will present future scenarios, and these future scenarios can help in the management of groundwater resources. So, these after a well calibrated and verified site specific model, which can reliably used for simulating or predicting future management scenarios, also these can be used for predicting impact of hydrologic and socio-economic changes. In the discussion of pollution in the groundwater and how it is done, so there these things matters a lot. If a site comes for hazardous waste or sewer waste or any kind of industrial waste, then we can predict what is going to happen, and these impacts of hydrologic and socio-economic changes, whatever is taking place, can be predicted. And therefore, a sensitivity analysis of developed model is performed. How it is performed? Before that, we will discuss that the purpose of this is to quantify the effects of uncertainty. So, through this what we are trying to know about uncertainty in the estimates of model parameters on model results. Whatever the simulated data are coming, how much certainty is there or how much uncertainty is there, and then only it becomes a perfect site specific model. Then it can be run for a longer time for various purposes in various other conditions also, when initial conditions are changing. So, this is done usually by perturbing the values of model parameters, one parameter at a time, by known amounts and measuring the effect of these variations on the model outputs. So, one by one these are done, and then finally you get the results. Like for example, if we make a small change in the model in the value of input parameters, and then it might produce a large changes in the model's output, and the model is said to be sensitive to that parameter, and that means to have a high influence on the model. And if large changes are being made and not significant changes are coming in the output, then that parameter is insensitive to the model. So, that is why this sensitive analysis is performed. So, in a large, when, as I have already said, when large changes are there, then input parameter should change in a small model. The model is said to be insensitive to that parameter, and then we can say that a parameter have a low influence on the model. So, sometimes if we are not getting data for that parameter which does not have much influence or insensitive, sometimes we can also ignore, because we have tested through sensitivity analysis that that particular parameter does not play any much role or does not influence our output of model. Now, whatever the knowledge we gained by doing all kinds of analysis, the sensitivity analysis particularly on a model, can help to elucidate the way which the model system functions. So, for each parameter one at a time we have to change, and we start with a small changes, then we keep testing each parameter. Similarly, all other parameters are changes one by one. So, that will develop a knowledge about that model system, how it is functioning, and then we will be able to identify those parameters of the model whose values need to be specified more accurately during the field investigations. So, once that is done, now we know which parameters influences our model most. So, while collecting the data in the field, care has to be taken so that we collect very accurate data. Now, finally, after even this sensitivity analysis, we come to the post audit, that everything is then assessed here at this stage. So, a more field data or information are collected beyond the model development period, and that is in future, and it is possible to compare the model predictions against the new set of field data. That means you are bringing a new set of data which have not been used in the model at all, neither in calibration or verification or any other stage. Now, a new set of data is coming and we are trying to compare that data with the model outputs, and will see that how the model has been performed, and this kind of process in groundwater modeling is called post audit. So, this may lead to further modifications, or I would say more tuning of the model, fine tuning of the model, refinements minor or major of previously developed site specific model, and due to significant changes in the system condition with time. See, for a site specific model, once it has been developed, but socio-economic conditions or other conditions changes, then accordingly the parameters have to be changed. Again the sensitivity analysis, validation, everything has to be done, and this keep happening in almost every area, because lot of developmental activities or socio-economic related activities are happening. And when the model was developed for a site specific model was developed, the initial conditions were there, the boundary conditions were there. But now, if a boundary condition has changed, then like for example, upstream of that area, a dam has come, or a reservoir or whatever, diversion of the channel has come. Now, the water level in the river has gone down, or no water is available. Then your boundary conditions have changed, and therefore, almost everything in the model has to be done. So, finally, few more points are there for related with the groundwater modeling, that the modeling is an excellent tool to understand or study complex hydrologic and hydraulic systems, and thereby by help formulate efficient water management strategy. Because modeling, as I have been saying, it is for prediction. So, if we predict very accurately, then these approaches, strategies, management studies becomes much better to manage our water resources, especially I am talking about groundwater resources. Further, modeling also facilitate efficient organization, analysis and synthesis of field data, what kind of data has to be collected and how efficiently, how accurately. But it is important to recognize that modeling is the only one component of a comprehensive hydrogeological study and not an end of itself. That means it is just one part, other parts are, many things are involved there. So, that is a different scenario. So, it is good in many sense, but it is not a substitute for everything. This is the point here. Modeling in conjunction with other tools and techniques can serve as a powerful tool for planners and decision makers. So, other tools, other data sets, obviously it will make these models and their outputs more reliable. So, a further important point here is the good modeling methodology, proper knowledge of the system under study. This is the key part in all kinds of modeling, that whatever the subsurface formations are there, what are their characteristics, what are the boundary conditions, what are the initial conditions. If these are well known, the good knowledge is there, then our model will perform very well. Perform means very well means whatever the prediction it will do, it will match with the ground data. So, as well as adequate and good quality data are required, essential to enhance the confidence in the modeling and analysis results. This is very important. I will give you a little different example from this modeling. Like modeling is done for the flow in a water, in a river or in a large river system, and about the discharge. And because that river, in the downstream of that river there is a reservoir, and that the water of that is a hydropower project. So, that water which is coming in the stream will be used for the generation of energy or electricity. So, the operator of such power stations or hydropower stations, they would like to know what is the discharge hourly in a river, so that accordingly they will run the turbine. So, for that purpose people have developed a site specific model for discharge, predicting discharge based on the snow melt, based on the ice melt, and spring water which is coming in the stream. Of course, that is influenced by precipitation. So, all those parameters are given in that input of that model, and finally every day or for hourly they predict the discharge in that stream which is having a hydropower, and then turbines are run accordingly. But if by some means, if the model discharge and the real discharge is different, then the operators of that hydropower project will have difficulties. So, what happens that whenever they are that this is not matching the model discharge and the real discharge, then again these models are recalibrated, relooked, revalidated, and after a lot of iterations, after many years of experiences, and then finally they get a perfect model which can very accurately predict what is the discharge going to come in the river. And this all is done before the discharge reaches that water or quantity of water reaches to the reservoir, which is the water of that reservoir is used for hydropower. So, these kind of models, this is how the models works, that keep changing, keep improving and developing such a highly reliable model. I gave the example of discharge. Similarly, that also these models will establishing the purpose of modeling effort at outset and establishing realistic expectations. Realistic means how accurate results it can produce, which are most effective utilization of modeling. So, if like example I gave, if discharge which has been predicted hours before, if it matches with the real one, then the full power or full water can be utilized to generate the maximum power from the turbines. Because we know that in next stage this much of amount of water or quantity of water or discharge is going to come. So, therefore, it can run appropriately. Otherwise, if these values are not known, then one does not know that what is going to happen. And also hydrogeologists also must establish appropriate expectation for the role of modeling in supporting group dynamics and decision making. Of course, all kind of modeling is for better decisions, for decision making processes. And these hydrogeologists should also, or groundwater engineers or hydrologists also understand modeling cost and its actual benefits. After a lot of cost, if a model has been developed and if it is not really predicting the way it should have been, then there is no use of developing such model. So, a wide as I have said in the beginning of this discussion, that at the end of this discussion we will be discussing few well known modeling software which exist to solve a different kind of problems related with groundwater. So, in order to select the best code or best program, first we have to fix the criteria, the demand should be formulated. What are our criteria? When we choose a model or a program or a model from whatever the available, then these points, the following points should be kept in mind. The first one is what code is the best in solving particular problem, because these softwares have been developed, these model softwares have been developed using different computer languages. So, which one is the best? If we can assess at initial stage before we enter in that modeling software, it is better. What are the data requirements? Models are groundwater model or any other models are data hungry. They need lot of data, they need the almost real time data to produce the future scenarios. So, what kind of data, if a model is requiring too much data, then the results are not going to match with the real one. So, the requirements for both code and problems that has to be assessed, computer hardware and supporting staff are required. Somebody has bought a software, modeling software. Now, what kind of hardware required by that software, and what should be the what kind of trained staff is required to run those models, and how much will the computer cost, code cost would be, that cost of the software. And of course, then this important question will come, how accurate the model is, and which is really representing the accurately the real world. This question will always be asked by the decision makers. So, whenever you are proposing a model in an organization or elsewhere, then the important question by the decision makers, by the managers or by an organization will be asked, okay, we are ready to invest this much money. Whatever you are saying towards hardware, we will train our staff and everything. But what would be the output from the model? It is going to match with the real one or not. So, accuracy part will always be asked, always be evaluated all the time basically. Anytime your model output goes bad, people will raise question on you, and therefore, that will compel basically, that will compel to develop better and better reliable models for river discharge, for groundwater flow and everything. So, this the accuracy part, as we have also discussed in our model section, that is very important. So, examples one after another, few well known softwares. So, MODFLOW. MODFLOW is very well known. MODFLOW is a USGS modular hydrologic model. Modular means some component for certain purpose you can buy, next you can buy, and it really it is a kind of extension of different extensions or modules. So, that is why it is called module. Initially you do not have the budget for buying the entire modules of MODFLOW. You can buy the initial modules which are essential and which suits your current requirement, current work, you buy that, and in future you can go for other modules. It is something like in ArcGIS ArcMap, you buy certain extensions initially, or it is also a modular software. So, many good softwares are generally being made as a modular software. As per your requirements, as per your budget, you buy initial thing and then keep adding different modules to it. So, MODFLOW is considered an international standard for simulating and predicting groundwater conditions and groundwater surface water interactions. And international standard, it has become in one day. It has been there since more than 20 years or more might be. But when people have started using it, they have found certain problems with the model, they have reported, and finally it has become a popular one, and so tested and calibrated one in that sense, and or utilized one, that it has become almost an international standard. So, there are various releases, various versions of MODFLOW. So, starting in 1984, 88, 96, 2000, 2005, then MODFLOW 2006, and first initial versions, the 3 versions of the code, MODFLOW 84, 88 and 96, were based on initial conceptualization of the program at groundwater flow only, but later on the other versions incorporated many other things. Now, window based MODFLOW, that is PMWin, is a complete simulation system for modeling groundwater flow and transport processes with the 3D finite difference groundwater model, and that is a MODFLOW. And there is a particle tracking model, that is PMFAT for Windows, and MODPATH, and then solute transport model MT3D, and parameter estimation program. So, these are the modules which one can buy along with the MODFLOW. And then there are libraries or labs, so MFLab, which stands for MODFLOW Laboratory. So, environmental design for efficient flexible groundwater modeling using members of MODFLOW suite, and that suite is, or extension you can say, is M3DMS. Visual MODFLOW or VMOD So, visual MODFLOW is a graphical interface. So, you are having a GUI, so it becomes much easier for the user to provide the data, and then also important part here it is open source groundwater modeling engine. So, in that way no cost is involved since it is open source. So, BMOD is also the industry standard for the same purpose, the groundwater flow, simulating groundwater flow and contaminate transport. So, in case of pollution studies this can be used successfully. Another type of model which is groundwater modeling system GMS performs groundwater simulations in a 3-dimensional environment. But remember, once we go from 2 dimensions to 3 dimensions, the input data requirement would be many folds compared to 2 dimensions. So, one has to keep this thing in mind. Now, groundwater vistas are there. So, it is a window based 3D groundwater flow and transport modeling software, and this GV is a pre and post processor for MODFLOW models. MODFLOW Surfact, see again is a powerful 3D finite difference flow and transport modeling code for analyzing subsurface systems. Another model is MODHMS, that is a interface with again is a kind of module of MODFLOW. So, it will interface easily with MODFLOW code, and it is physically based model, spatially distributed model, and a conjunctive subsurface modeling framework, and which will give water resources managers unsuppressed capability to simulate the complete hydrologic cycle and to take into account of all relevant processes and hydrologic interaction. So, that is in that way it incorporates almost all requirements for the modeling or of the modeling. Now, FE flow or the finite element subsurface flow system, and this simulates the flow, mass, heat transport and processes in the subsurface. So, where people are concerned with temperature and in hot springs and other things, similar kind of models can be adopted. Enables users to analyze interaction below the land surface in subsurface condition, including underground structures, tunnels and other types of excavations. So, in mining industries such models are also being used, predict potential water quality issues in groundwater and provide remedial strategies, and also model geothermal initialization at any scale and depth. So, as I have said, for hot springs or geothermal energy kind of thing, because it handles the heat transport processes as well. It also allows to investigate groundwater surface water interaction by coupling FE flow to other software like MIC, which is surface water models. MIC is very popular for surface water modeling, but we are, so it will allow you to develop that kind of groundwater surface water interactions by mixing or coupling with FE flow to other flow surface water model like MIC. And also this will estimate ground subsidence, which is also becoming a big problem where over exploitation of groundwater is happening. So, this kind of model will predict that if such things continues, what is going to happen to ground subsidence, predict pumping rates and stability issues in geotechnical and mining projects. So, in mining project this can be very good, because subsidence in mining is a very another thing, in especially I am talking about subsurface mining like in coal mines in Jharia and Raniganj in Jharkhand and West Bengal respectively. So, there the subsidence in the cities, I gave in earlier discussions, I gave the example of Kolkata city. Now, important part here is that whatever the estimates which we made through about the groundwater subsidence, these can be validated using SAR interferometry technique, or in short we say INSAR, by using radar remote sensing. So, by which we can validate that whether the estimates which are being provided by this FE flow model are matching with the real with the SAR interferometer, because few millimeter subsidence or few centimeter subsidence may not be felt by the people on the ground if there is no differential subsidence is happening. But by the SAR interferometry technique, we can validate results of these this kind of flow, which are good for ground subsidence estimations. Another one is the MOD HMS. So, this is an interface between again MODFLOW code. MODFLOW is the basic software, and many along with many models you are seeing that this is an interface. This can interact very easily, and data from one to another model can work, or from one extension to main model can work very easily. Again, this is a physical base, spatially distributed, conjective, subsurface water and other things are there which can be used. Finally, I am reaching to this open source groundwater software, which is MODFLOW one water hydrologic flow model is the MODFLOW 2005, which is based on integrated hydrologic model designed for analysis of conjective use of groundwater, of course, and management. And there is another integrated water flow model, is a computer program used for water sources management or water resources management and planning within a basin. It calculates the groundwater flows, soil moisture movement in a topsoil, stream flow, land surface flows, flow exchange between the groundwater streams and land surfaces as generated by rainfall, agriculture, irrigation, municipal and industrial waste. And these are the important point here is these are the open source softwares. So, because the cost is not involved and lot of help, lot of discussion groups on the net can be found. So, if one develops expertise and then in-house or sitting in a house having a small computer or a laptop can develop the expertise in such models, because the initial cost is not there at all, at least for the software, because these are the open source software, and somebody is good in programming or coding can also modify their program, so they becomes very befitting for a site specific modeling. Now, another thing is the weathering research and forecast model, because meteorology affects our hydrologic modeling. So, those are there also community based open source again model coupling framework and designed to link multi-scale models and other things are there. And there is another one is PowerFlow, is a numerical model simulating the hydraulic cycle with the bedrock to the top of the plant canopy. And they are very because in open source, so there might be some limitations also with the open source softwares. Anyway, and there are some other examples are there. DFN and works is a parallelized computational suite to generate 3-dimensional discrete fracture network or DFN and simulate flow and transport. So, for a specific regions, a specific software can or open source software can also be adopted. Before that, if you venture in this one, before that one should go through the entire literature, what are the key benefits of using that particular model and what are the lacunas, what are the limitations of, because each model will have some limitations. Also, before adopting a model, one should also know what are the data requirements. So, now we are almost reaching end of this discussion, and here one example is here that drawdown in prediction scenario 1, 2, 3 in starting from left to right about Yamuna Krishni sub-basin sorry. So, here it is drawdown is getting predicted for different time, and what you see that see the drawdown is increasing in a particular area, and rest are also showing changes here. So, when we are approaching say dry spell or dry season pre-monsoon areas, see the drawdown is showing red areas, otherwise in the just post monsoon things are in a much better shape. And aquifer vulnerability map of the Yamuna Krishni sub-basin, the same basin which I showed in the previous slide is also there. So, vulnerability index can also be estimated for out of these groundwater modeling as shown here. So, here these aquifer vulnerability map showing that which are most vulnerable areas and which are less vulnerable areas. So, with this I end this discussion. Thank you very much.